Hello, it's Stan from MathWorks, and today I'll be showing you how to create a function in MATLAB. Let's say we're interested in calculating the displacement of a moving object over a 10-second period. One way to accomplish this is to write a function which will multiply time, we'll say 10 seconds, by velocity, specified in meters per second. In order to make this function, we'll need 5 core elements: the keyword function, the outputs, a name for our function, the inputs, and the keyword end. These 5 components will be used in nearly every function we make. So to start, we'll hit new and we'll go to live function, and that'll actually create the 5 core elements for us. From here, I'll change our function name to find displacement. I'll change our input to velocity. I'll change our output to displacement, put the outputs in square brackets, and then we'll fill out the body of the function. So in our case, displacement is going to be set equal to velocity times our time period, which is 10 seconds. Put a semicolon there. From here, Control S to save the function, and we'll save it as finddisplacement.mlx and hit save. To run our find displacement function, we should enter the following in the command window. The output, which is displacement, set equal to the function name, and our input, which in this case I'm going to say is 9 meters per second, to find the displacement. We hit enter and we get our 90 meters. Now that we understand the basics, I want to take a minute to discuss why we use functions in programming. At a basic level, a function is a task or set of tasks which are performed on some input to transform it to a desired output. Usually, these tasks or set of tasks need to be performed multiple times, so coding the tasks by hand each time would be time-consuming and make the code unnecessarily long. For example, imagine you are tasked with making 1 million cups of coffee in a year. You generally repeat the same process for each cup of coffee. You grind the coffee beans, you heat up the water, you soak the beans in the water, you filter the beans from the water, and then you pour the coffee into the cup. Since these specific set of tasks need to be performed multiple times, 1 million to be exact, it would be good to automate the procedure. Instead of trying to make 1 million cups by hand, you can make a robot which would take in the amount of cups to make and all the ingredients and output the cups of coffee. Now, the robot here is actually acting as a function. It is performing a defined set of tasks for a given set of inputs and transforming the ingredients into a warm, caffeinated output. Now that we understand why we create functions, let's try and make our find displacement function more useful. Now let's say we want multiple outputs, displacement and acceleration. For this, we're going to need an additional input as well, since the acceleration equation needs both an initial velocity and a final velocity. So we'll add a variable named initial velocity. From now on, we'll be treating the velocity variable as the final velocity. To accomplish this task, we'll first add the additional input to the function, like this. Initial velocity. And then we'll add an additional output to the left side of the function call, next to displacement. We'll call it acceleration. Finally, we'll update the equations in the body of the function. You can see we've added an acceleration equation as well as updated the displacement equation. Now let's practice calling this function from the command line with an initial velocity equal to 0 meters per second, a final velocity equal to 10 meters per second, and a time period of 20 seconds. We'll ask for 2 outputs, displacement and acceleration. We'll hit enter. As you can see, we've received our requested outputs and our function works as expected. As an exercise, you can try and incorporate the force equation into our find displacement function. In order to do so, you'll need to add an additional input, mass, an additional output, force, and an additional equation to the function, force equals mass times acceleration. If you have a few minutes, give it a try. I want to take a minute and talk about the scope of variables within a MATLAB function. Scope of a variable is where it is able to be interacted with. Let's say we define an intermediate value for our find displacement function. Let's call it delta v, where delta v is the velocity minus the initial velocity, and we'll substitute it into the acceleration equation. We'll save our function. Now if we use the same call as before, hit enter to run it, and we check our delta v value, we get an error, unrecognized function or variable delta v. The reason we get an error is that delta v is only defined within the function workspace, which, when the function finishes, is removed from memory. Only the outputs are passed from the function workspace to the base workspace. If you'd like, you can add delta v as an output and confirm that it will be defined after the function has run. Now that we understand function basics, I would like to discuss what we should and shouldn't call our custom functions. To start, naming your function after any built-in MATLAB function is a bad idea. For example, if I name my function plot and save it as plot.m, anytime in the future that I go to use the built-in plot function, my custom function will run instead. Some good practices to follow when naming functions are listed on the screen. In general, function names should be short and meaningful. Overall, the best name for a function is one that communicates the usage of the function without the user having to read the actual code. Now that we've covered function naming, let's move on to a more advanced function. Let's now assume that we want to model the displacement of a projectile. Our goal is to find the optimal launch angle. Our inputs will be as follows: velocity and a launch angle in degrees with respect to the ground. For outputs, we'd like the following: max height, time in air, total horizontal displacement, a plot of the position of the projectile over time, as well as a plot of the launch angle versus the total horizontal displacement. Here's the skeleton of it. We'll go ahead and save the file as modelprojectile.mlx. Off screen, I've filled in our projectile function using the equations of projectile motion. The code for the full function will be available in the description for this video. One part I'd like to point out is the call to subplot within the function. This will create a figure with multiple plots, one for horizontal versus vertical displacement, and one for launch angle versus horizontal displacement. At this point, I'd like to run our model projectile function multiple times for different launch angles to see which is the optimal. In order to do this, I'll need to create a script that calls the function and combines the plots of each run. Off screen, I've created a script called projectilescript.mlx. To start, I've created a loop that'll run our projectile function 100 times. Within the loop, I write out the call to our model projectile function with the following inputs: 100 for the launch velocity and a random number between 0 and 90 for the launch angle. Following that, I've created a vector to store each of the values of interest: our max height, air time, horizontal displacement, and the launch angle. After the end of the for loop, I've created a table which captures all of this information. I've also released the current plot using hold off so we can view our results. If we go back into modelprojectile.mlx, you'll see that after each call to plot, I inserted a hold on to retain the current plot. If I hadn't done that, each iteration of the loop would have created a new figure, which was not something I wanted to do. Let's run projectilescript.mlx and see the results. Unsurprisingly, 45 degrees appears to be the optimal launch angle. The plot on the left shows the path of the projectile in terms of vertical and horizontal displacement over time for each of the 100 runs of the function. Finally, our table contains all the pertinent information from all 100 runs. A final observation is that for plots, no output argument in the function is necessary. However, if you wanted to continue to use the figure handle, you would have had to include it in the output argument. As you can see, we were able to save a lot of time and a lot of copy and pasting by using a function to calculate the max height, air time, and horizontal displacement for 100 instances of a projectile. Without the use of a function, this would have been a very tedious task. Well, that's it from me. If you'd like any more information on any of the topics discussed in today's video, please check out the MATLAB documentation. We'll see you next time.